Hello and welcome to Earthquake Tip number 17. My name is Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Mukti, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to comprehend language to our professionals who are in the field designing and constructing structures, especially our engineers and architects. But before we start, let's make a pledge. Any new structure we design or build must be earthquake resistant. This earthquake tip number 17 will explain you how do earthquakes affect reinforced concrete buildings. So far, we have discussed brick masonry and stone masonry buildings, their seismic behavior, and earthquake resistant measures to be employed in these kind of buildings. Now let's move to reinforced concrete or RCC buildings. In recent times, as you all know, reinforced concrete or RCC buildings have been very common uh, in our country, particularly in towns and cities. These RCC buildings consist of two primary materials. One is concrete and other is steel or reinforcement. Concrete is a mixture of cement, sand, and crushed stone or aggregates with predetermined amount of water. Concrete can be molded into any desired shape, and steel bars can also be bent into any shape, and therefore structures of complex shapes are possible with reinforced cement concrete, and that is why this is most popular construction system across the globe. A typical RCC building is made of horizontal members, namely beams and slabs, and vertical members, namely columns and walls. And these are supported by foundations that rest on ground. The system comprising of RCC columns and connecting beams is called reinforced cement concrete frame or RCC frame. The RCC frame participates in resisting earthquake forces. As you already know, earthquake shaking generates inertia forces in the building proportionate to its mass. Since most of the building mass is present at the floor level, that is at the slab level, earthquake-induced inertia forces primarily develop at floor levels. These forces travel downwards through slabs and beams to columns and walls and then to foundation, from where they are dispersed to the ground. As the inertia force accumulate downwards from the top of the building, the columns and walls at the lower story experience higher earthquake-induced forces, as you can see in this figure 1. Therefore, always remember, lower story columns experience higher forces and shall be designed to be stronger than those in stories above. Now let's see how floor slabs and masonry walls participate in earthquake-induced shaking. Floor slabs are basically horizontal plate-like elements which facilitate functional use of buildings. Normally, beams and slabs at one story level are cast together. In residential multi-storied buildings, thickness of slab is 4.5 to 6 inches. As you can see in this figure 2a, when beams bend in vertical direction during earthquake, these thin slabs bend along with them. And when beams move with columns in horizontal direction, the slab usually forces the beam to move together with it, which is shown in this figure 2b. In most of the building, the geometric distortion of slab is negligible in horizontal plane, and this behavior is known as rigid diaphragm action. As engineers, while considering earthquake resistant design, this action must be taken into account. Now let's see the walls. After Columns and floors in RC buildings are cast and the concrete hardens. The vertical spaces between columns and floors are usually filled with masonry walls to demarcate a floor area into functional spaces, that is the rooms. These masonry walls are also called infill walls and they are not connected to surrounding RCC columns and beams. As you can see in this figure 3, when columns receive horizontal forces at floor level, they try to move in horizontal direction, but masonry walls tend to resist this movement. Due to heavy weight and thickness of these walls, they attract rather large horizontal force. As we already know, masonry is a brittle material and therefore these walls develop crack once their ability to carry horizontal load is exceeded. Let's consider these infill walls as sacrificial fuses in buildings. Means they develop cracks under severe ground shaking but help share the load of beams and columns until cracking. The earthquake performance of infill walls is enhanced by mortars of good strength, making proper masonry courses and proper cracking of gaps between RCC frames and masonry infill walls. However, remember, an infill wall unduly tall or long in comparison to its thickness may fall out of plane, means in its thin direction. This out of plane failure can sometimes be life-threatening and should always be avoided. Also, the infill irregularity in the building cause other ill effects such as torsion, stiffness irregularity, short column effects, etc. Now you can see this figure 4, which tells you how horizontal earthquake effects are different than the gravity loads, that is vertical load. As you know, gravity load is due to self-weight and contents of building. It causes RC frame to bend, resulting in stretching and shortening in various locations. That means tension is generated at surfaces that stretches and compression at those that shorten, as you can see in this figure 4b. Under gravity load, tension in the beam is normally at the bottom surface of the beam in central location and is at the top surface at the ends, as you can see in this figure 4c. Whereas the earthquake loading causes tension on beam and column faces at locations different from those under gravity loading. The relative levels of this tension, that is bending movement, are shown in this figure 4d. The level of bending movement due to earthquake loading depends upon severity of shaking and can exceed that due to gravity. Therefore, always remember, under strong earthquake shaking, the beam ends can develop tension on either of the top and bottom faces. Since concrete cannot carry this tension, steel bars are required on both faces of beams to resist reversal of this bending moment. Similarly, steel bars are required on all faces of columns too. So to conclude, for classical vertical design, steel bars are required only on faces where tension is being experienced, whereas in earthquake resistant design, tension can occur in both the faces of beams and in all the faces of columns, and therefore steel bars are required on both faces of beams and all faces of columns for earthquake resistant design and construction. Now let's look at this figure number 5. For a building to remain safe during earthquake shakings, column which receives forces from beams should be stronger than beams, and foundation which receive from column should be stronger than columns. Further, connection between beams and columns and foundation should not fail, so that beam can safely transfer forces to columns and columns to foundation. As you can see in this figure 5a, if this strategy is adopted in earthquake resistant design, damage is likely to first occur in beams. When beams are detailed properly to have large ductility, the building as a whole can deform by large amounts despite progressive damage caused due to consequent yielding of beams. On the other hand, as shown in this figure 5b. If columns are made weaker, they suffer severe local damage at the top and bottom of a particular story. This localized damage can lead to a collapse of a building, although columns at stories above remain almost undamaged. So always adopt strong column, weak beam strategy for earthquake resistant design. In order to design RCC buildings, Bureau of Indian Standards have published three codes, namely IS 1893, which is the Indian Seismic Code for calculating earthquake forces, IS 456, which is Indian Concrete Code for design of RCC members, and IS 13920, which is Ductile Detailing Code for detailing requirements. This is all about earthquake tip number 17. You can download the tip from www.bmtpc.org. The next earthquake tip, that is tip number 18, will be on how do beams in RC buildings resist earthquakes. Thank you.